Good afternoon, sir, and welcome back. So now we have a lecture by Professor Netan Dogra from King's College London, and he will be speaking on Chabauty, Coleman, Caro, Pasten bound in higher dimensions. Thank you very much.
Yeah, well, I'd like to again thank the organizers for putting this event together and giving me the chance to speak again. It's been a really wonderful week. Really enjoyed it. So I've got some good news and some bad news. The good news is I'm not going to speak for a full hour. So, and if you start smelling the delicious food outside, don't worry, I'll try and finish by 1:15 at the latest. We'll get to bad news in a second. So what I'm going to talk about, I should say, actually, is work in progress. So it's something which is, I think it all works out, but I haven't written down all the details. And I've got a paper. So ultimately what it's going to end up being is some kind of upper bound on something. And I think the upper bound is right, but it may be that there's some progress and the upper bound gets better, and it may be that there's some work and the upper bound gets worse. And yeah, so what am I going to talk about? And this is the bad news. The bad news is, and this is I realize this is my 7th hour of talking to most of you, and I'm still not saying anything about modular curves. So I feel very bad about that. So okay, so a partial excuse I can make is, what am I going to be talking about? I'm going to be talking about subvarieties of abelian varieties. So I'm going to have some x inside A. For me, A is always going to be a simple abelian variety. And X, let's say of dimension G. X is going to be proper subvariety. You might want. It's geometrically irreducible. And it's going to be of smaller dimension. Yeah, well, I said it's probably. But let's say it's of dimension B. And then it's a theorem of faultings. Amazing theorem. So let's say if these are all over Q, the set of rational points of X is finite. Amazing theorem that he proved using Diophantine approximation results. And subsequently was shown that you can actually even do some kind of quantification of this, which I'll discuss. Now, this type of setup does have some relevance to modular curves, so that's a kind of partial excuse I can give, which is, and I think we'll hear a very nice talk about this by Michael Stoll tomorrow. You could try and understand degree D points on modular curves, like x1 of n or x0 of n, or the other ones we heard about this morning from Samuel. And degree D points you can interpret as rational points on the d symmetric power of your modular curve. So, so I'm going to talk about some kind of tools for understanding how you can understand this number. And it's not clear to me that really the setup that I'm interested in is really directly relevant to the setup that the type of problems one is trying to solve when you want to understand degree D points on modular curves. But I do think that the ideas that I'm going to describe, hopefully, many of which I should say are inspired by some work of Caro Pasten, which I'll describe, offer an interesting new perspective on this general problem. And maybe, hopefully, there's something in there which has some relevance. So before I get to Caro and Pasten's work, I'm going to describe some more general context on the problem. So I want to talk about bounding the size of this. And I should say that the kind of best known general result we have, which does build on work of other people following on from faultings, kind of coming up with explicit estimates, but now we have this optimal result, which is a special case of something called a uniform model Lang. This is an amazing theorem of Gao, Gay, and Kuhner. So what they do is actually much more general than this. This is just a special case of their results. But they show that. So I should get my quantifiers right. Well, oh, I guess it's implicit from the statement. You can bound this by some constant. Sorry, it's subscription. So the idea is that this degree, you fix an ample line bundle on your abelian variety, and you just take the degree of X as a subvariety with respect to that. And the G is the dimension, and this just depends on. So this was a big open conjecture in the field. And so this was a generalization, I should say. Of theorem of Dimitrov, Gao, and Haberger. The curves. Which essentially has exactly the same statement. Where A is then the Jacobian. So this is the best general result, but in the case of curves, we know if the rank is less than the genus, then you can get an improved estimate, which is improved in two ways. First of all, this C is, I think it's fair to say, an ineffective constant. So some people in the field say that in principle, maybe with a lot of work, you could come up with some kind of explicit C, but there's an acknowledgement, I think, that it would be humongous. And whereas for curves, you can actually, for curves of low model variance, so where this number is small, you can get a very good dependence on, say, as you vary G, you can get a linear dependence on this rank. And that's the theorem of Coleman, which we've heard a little bit about already. So now, let's take X to be a curve. And nice. Curve of genus E greater than 1 over Q. And suppose that the rank, the Jacobian, less than the genus. Size of this is bounded by the number of FP points. Oh, sorry, yes. And maybe I want to make two statements actually. E greater than 2G minus Q, I think, is a prime of good reduction. And the size of this is bounded by the size of this. That's 2G minus 2. And actually, a nice thing about this, which will be relevant for later, is that you can also deal with the case of smaller p's, so that you get a slightly weaker bound. You get, if I remember rightly, something involving log p, and then exactly the same expression. going to say as a build up for the high dimensional case, I'm going to say a bit about how this argument goes in a second. Okay, so now I can tell you about this. So this theorem of Coleman was from the 80s. Now I want to talk about the theorem of Caro and Pasten, which was just from the past couple of years, and I think was a really kind of important and beautiful result, which I think is important not just for the statement, but also for the ideas they introduced. And I think it gives a really interesting new perspective on the Chabauty-Coleman method. So their setup is they consider X to be a surface inside A, which they consider the case where the rank of A is 1. So less than or equal to 1. Then, well, so Jennifer actually mentioned that theorem in one of her talks, and as she mentioned, there are a few different statements, but I'm not going to go through all of them. It's a prime of good reduction. Well, so they want an ample line bundle A. They also want P to be bigger than some number, which is very much analogous to what came up here, but the number gets bigger, so it's remember rightly. Sorry, notation. N is a G. E. Where these quantities here, where we're taking the degree, this is all in the sense of intersection theory. Oh, yes, they have that assumption. And finally, they want that the special fiber of A is geometrically simple. So AFB bar is simple. So sorry, and P is a prime of good reduction for both X and A. Then the size of X of Q, it's a really nice formula, that most of the sides of XFB plus P minus 1 over P minus 2 times P plus 4P to the half plus 3 times here, which is again just an intersection number of line bundles. So it's intersection number of the canonical bundle of X with itself. And as I said, they have a number of other results. So I think they have also improved results when dimension of A is 3. And they have some other results where they weaken the condition of the special fiber being simple. But they impose a condition that the special fiber of X doesn't contain an elliptic curve. And so for all of this, for this and more, I advise you to look at their paper. Okay, so the result that I want to talk about today, which, as I said, is a work in progress. So I'm going to give it a star. I'm going to give it 2 stars just to clarify that it doesn't quite have the same status as, well, in importance, but also in terms of theoremness, doesn't have quite the same status as the other results. So, so X inside A, as in, I guess, the faultings and theorem, so no assumptions about the rank of A or the dimension. Suppose X has good reduction at P. P again has to be greater than 2. I mentioned that here, yeah, P is greater than 2. Then this number is at most sorry. It's going to write D times log, but to me, D times log always looks like D log, so I can't write that. D. 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 To the D. Or brackets. FP. Plus 2D minus 1. X. D plus D to the D. Oh, where M is equal to the maximum from I equals 1 up to D, the degree X to the I. So some of these numbers we'll see where they come up in a kind of discussion of the ideas in the proof. So it's not so important exactly what they are. So now I want to go on to describe the ideas in the proof, and there's a real kind of continuous thread in these 3 theorems, kind of similar ideas coming up. In each case. Maybe before I go into the proof, so I'll start by explaining Coleman's proof, but maybe if I just go back to this theorem I just stated, this last theorem, so remark, so it's a question. Well, actually, no, sorry, maybe sorry, that would be better to mention later. Oh yeah, idea of proof. So now I'm going to be slightly sloppy, and I'm going to use, I guess, my X and my A are now going to be models over Z round brackets P, but we can forget about the rational structure and just say that X and A are now going to think of them over ZP, and sometimes I'm going to talk about their rational points. Then what we get from the Chabauty-Coleman method in all cases is that there exists omega 1 up to omega D in H naught X omega X over ZP, which are linearly independent. Oh, sorry. Very important thing I forgot to say. So here, the rank was less than or equal to 1. I should have said the rank of A got to be less than or equal to G minus D. Otherwise, even in the case of curves, this would be quite a striking result. So in that situation where you have a kind of defect of D in the rank of A compared to the dimension of A, then that means that you get, sorry, maybe in A, sorry, which are linearly independent, maybe let's introduce some notation. So maybe let's call this map F, the inclusion of X into A. Then X of Q is contained inside the set of all omega I equals 0, A equals 1 to D. With respect to some basis, and where these are the Coleman integrals that those of you who were here last week have heard a lot about, and I'll say a little bit about them later. Well, I should say that just because this is a convention slightly different from the one that Caro and Pasten use in their paper, for me, the pullback of this differential is an element of differentials on X. This is an important distinction because at some points in the argument, it's actually also natural to think of the pullback of a differential as an element of H naught of X of the pullback of the sheaf of differentials on A to X. If there's a normal bundle distinction, which will come. Okay. So that reduces to bounding the number of zeros of these analytic functions. And these are locally analytic functions, but as you can see in the bound, our bound involves some kind of counting over all FP points. So we can actually just fix some FP point of X. And so recall X was, so for us, we can think, today we can just think of X as being a set of ZP points, although we discussed how it's more than that. So it's a reimage of X. And then I'm going to define this thing, zero set of these differentials to be zero set of these differentials, but sorry, pulling them back. Maybe I'm going to kind of drop the pullbacks from now on. I'm going to write omega I or was star omega I. So, ease notation intersected with X. So actually, I think I'm going to want to maybe just reserve a board just for pictures of this, because there'll be a few different pictures. So inside here we have X. And then we have kind of, we have the tube. Here we have the tube of X. And so we're going to study the intersection, I mean, this is by definition, is the intersection of the zero sets of two functions. So we're intersecting kind of maybe zero set of the first one, for example, so this is in dimension 2 with zero set of the second. The world's greatest picture, but there'll be some more. So what happens in Coleman's theorem? When d equals 1, so then d of omega equals the zero sets. So in closed ball of radius 1 over p of some function and the size of this is the same as the length of this, some slope of the Newton polygon of this function. So if you haven't seen Newton polygons before, basically all that's telling you is that I can understand the number of zeros just by estimating the valuation of these coefficients. That's the point. The adic valuation of the AI. And so on the other hand, if I differentiate this function, so df by dt, or either we could say df is equal to omega. So when I differentiate this function, the power series expansion I get, so I times some ai, t to the I, times dt is actually in zp double brackets t times dt, because it's the expansion of this integral differential omega, and its reduction mod p expansion, the adic expansion of omega mod p, a thought of as an element h naught x. Okay, but so the number of zeros I'm saying is basically the length of this slope. So actually, it should be an equal. So basically, long slope implies lots of zeros mod p. That's how this building of the Newton polygon from these valuations works. That pops straight out. But these things, theories of omega mod p are bounded by Riemann. And so maybe I'll just say, where does the p greater than 2g minus 2 condition come in? Well, one way of phrasing it is that basically if p is greater than 2g minus 2, then because omega can have a zero of order at most 2g minus 2, you don't ever have to worry about the pth term of this series here. So this was, oh, sorry. Because at the pth term, something funny happens, because the valuation of f is actually going to be smaller than the valuation of this because you're dividing by p. we divide by p in expansion of omega before we get to Riemann-Roch bound. However, you can still estimate how much you're dividing by p, and that's basically where the log p comes in. So one way that you could phrase what you have to do differently, which I think is, maybe it's not the most obvious way to phrase it, but to some extent it kind of motivates the generalization, is that we could say that to generalize this, what you have to do is you have to work mod p to the n. You lose too much information if you just work mod p. Just think of omega as a differential mod p. You need to throw some more information in. Okay. So now I want to give a reformulation of this, kind of geometric reformulation. So now let's suppose that I had abelian, maybe I should call the abelian variety B. Or actually, no, I could just don't even have to have an abelian variety. Let's just suppose I've got some complex algebraic variety. I've got some global one form. So then we could take the complex zeros of this integral, relative to some base point. Well, it doesn't really make sense because over the complex world, as we've seen, this depends on the choice of path. But you could pick some small neighborhood, which is contractible, and just look at that complex manifold you get from integrating on that path, on paths in there. And this will give you a complex submanifold of Y. And it has the property that, let's call that submanifold V. It has the property that when you pull back omega, it vanishes. Almost basically, it's a defining property. So actually, what this so let's say this is vanishing of omega. So it's set where omega equals 0. So the zero set of some differential you should think of as being where the differential is equal to 0 when you pull back. And actually this, for example, in the complex world, this is giving you some kind of foliation of your variety. And that foliation is exactly described by vector fields dual to this differential form. Okay, so our situation, remember, was that we had V of omega, which I really want to think now of as, so V of omega I want to think of as inside Z. So it's some finite set of points. Now, usually when you have a set of points, it doesn't really make sense to, so in particular, I want to think of it as a scheme. So finite over ZP. Set of points, then you're not going to get something interesting by looking at what you get when you pull back a differential to it. Except because we're over ZP, this thing is not equal to 0. That's kind of essentially what was going on in Coleman's proof. So, e.g., simple example. Calculation correctly. This is so you should really think of this as a geometric object where you can do some kind of calculus and you can study differential forms. So then we could say, well, this is the set of points we're interested in, and what we want to do is we want to pull back our differential form to this set. So we have the same story. And well, the answer is not necessarily. So e.g., what example did I take? We could take, so I guess this is taking omega to be equal to dx over 1 plus x on gm over z2. Then in the discrete 2, we're going to get the points 0 and 2. So, or I guess, yeah, 0 and minus 2. So we get and then when we pull back omega, if I've done my sums correctly, not 0. So we saw that this is the we saw that this is non-zero from this example we did before. But okay, so I did this for p equals 2, and this is again another one of these small primes phenomena. Okay, so I'm really ready to explain the generalization to higher dimensions. So what you could do is you could take, again, we're still talking about curves, you could take z of omega inside x, which you define to be the vanishing locus of this section of your vector bundle, of your line bundle differential forms. And then you suppose you have lots of points. Lots of points. Well, then this will give you some map from some big N. This will give you a map from here to here inside your V of omega being included in here. So it gives you an FP of x modulo x to the n point. So the picture to have in mind, only colored chalk, maybe it's too far away, is now, so now we're in the one-dimensional setting, I guess, but maybe it's good to draw it as like this. So we're assuming that we have, because we have lots of points mod p and we get this big kind of space of differential forms, we kind of think of V of omega as a bit like a kind of thickened point. So even though it's a finite set of points, kind of thickened in the sense of algebraic geometry. And that thickening means that actually, if we now define, it's probably very difficult for filming. So if we now define, oh yeah, sorry, I've defined z of omega, sorry. Then we have this space inside here, z of omega. And we don't necessarily get that this is contained in here, but we have actually a big intersection. Sorry, this would have been a bit easier to see with colored chalk. So z of omega intersects V of omega is big. So it's roughly speaking, it contains an FP of x modulo x to the n point. But Riemann-Roch gives us a bound on this thing is small. That kind of gives us a bound on. Okay, and actually, in this language, almost all the ideas that you need in higher dimensions are present. So let me now kind of explain roughly what Caro and Pasten do. So now we're working with the surface and we have two functions. So we have some surface S, sorry, I was calling X, and then we have two functions, omega-1 and omega-2, and we want to understand their common zeros on some residue disk of X. And I guess maybe some intuition for what they do. Maybe let's call this function F1, this function F2. Is something called an elementary result, multivariable version of Hensel's lemma, which I think is also can be viewed as a special case of some of the lifting results, which were kind of related to the rigid cohomology results I was talking about, but it's much more elementary. So it just concerns when you have F1 up to Fn in Zp of x1 up to xn. And you suppose that the Jacobian doesn't vanish mod p, so that's not the Jacobian that we usually talk about, but this is the Jacobian of differentials of the Fi's by the dxj's. So vanish at the central point of this power series at the unique point. Then 1 up to Fn have at most one common zero. Inside so if we were to rephrase that in a kind of geometrical language, what that's telling us is that we should look at zeros of this 2 form Z. And that's exactly what they do. So maybe I should just mention in words. So I mentioned that their condition is stated for the case when the rank of A is equal to 1. And that's because they make a very nice observation that if the rank of A is equal to 1, then instead of maybe I'll just write it, rank of AQ equals 1, instead of working on X, you can work on the closure of A of Q in A, which you can think of, I mean, in the context we're working with, is going to be some one-dimensional rigid analytic space. So this is actually a very similar trick to one which, I mean, I believe, kind of more like Chabauty's original perspective, and was certainly utilized by Flynn in his work on Chabauty, and also more recently, Adixoven and Lido. Instead of pulling back to the curve or the sub-variety of an abelian variety, you actually pull back to the closure of the rational points. But we're not going to do that. So instead, what you do is you study the intersection of V of omega-1 and omega-2 with what I'm going to call Z of omega-1, omega-2. So that's, I'll call it Z naught of, this is, by definition, is the vanishing locus of. And why do they do this? So basically, you can make the same argument I made before, that if B of omega 1, omega 2 has lots of points, then you get some kind of P of x modulo x to the n point of, or an Fp of x modulo x to the n point of this. So you get some version like this. So I guess I'm just doing. Okay, but now, so by definition, everything in here, well, apart from this small primes issue I mentioned, has the property that when you pull back omega 1 and omega 2, they vanish on here. So that means when you pull back omega 1 and omega 2, they vanish on here. But now what does this mean for, maybe let's call this ring, we'll call it R bar n. That's subjected onto by omega of x over the zp modulo omega 1 and omega 2. But I mean, generically, omega 1 and omega 2 are going to, as an outside a closed subset, omega 1 and omega 2 are actually going to generate x. And whereas this thing is very big, actually, if you think about it. Support. I guess what I would call R bar n minus 1. So that implies that you actually get a spec R bar n minus 1 point of z of omega 1 omega 2 intersect B of omega 1 omega 2. But then now I could pull back to this point I have here and note that on this omega 1 and omega 2 also vanish. And they have to vanish to very large order. And that means that if I define, say, Z1 of omega 1 omega 2 inside Z omega 1 omega 2 to be the vanishing locus of the pullback of omega 1, when you pull it back to here, then you're going to get some big points. It will be some, roughly speaking, modulo some technicalities of Z1 omega 1. But now this thing here, we can, so certainly for large primes, bound again using Riemann-Roch, but now it will be Riemann-Roch for surfaces. So you can basically bound it by intersection theory. And maybe it's clear from, sorry, I've run over my stated time. So maybe it's clear from what I said that from the numbering that I want to keep going with these z's. And so that's what you do. So for general dimension, you can kind of inductively define things like this. And then you end up kind of trying to bound the size of ZD omega D. And I'm just going to say one last sentence. There's one other subtlety, which is that normally over the complex numbers, when you pull back a one form on a simple abelian variety to a subvariety, one form will not vanish, but one forms can on A of FP can vanish on these subvarieties at I. This was kind of, I think, first observed by Abramovich. You have to kind of understand that phenomenon as well, but that's another story. So sorry for not fulfilling my promise, and thanks everyone for your attention.
You, Nathan. Are there any questions or comments, clarifications, anything if you like?
For the, you assume at first that the A is simple,
Mhm.
so that the Faltings statement gives this. Let's say you don't assume A is simple anymore. So you have a Faltings set. Assume you know this as well. X of Q is there's an infinite part coming from the Faltings set, but you can project to every simple factor. Do you have an idea of what the statement could look like? Try to deal with this.
Yeah, I mean, I hope that it would be possible to say something, but yeah, I haven't really thought about how things change when you have to pay attention to all the sub-right. I mean, a similar thing comes up when people have tried to apply Chabauty-Coleman symmetric powers and things. Practice.
I was thinking specifically in the case of a square of a curve with a prime variety. Maybe that's.
Yes. Well, I mean, the statement one would dream of is that you somehow can both bound the number of exceptional points and also the degree of the positive dimensional component. But I think bounding the degree would probably involve different techniques. But maybe you could have some argument just for the exceptions. But I don't have one.
Yeah, any more questions?
But I think in the statement of your theorem, you only had the assumption of good reduction.
Oh, sorry, that was, yeah, then you didn't miss something, I missed something. No, yeah, I want A to have good reduction. In fact, I think it's reasonable to imagine it might be possible to do it if A had good reduction and X didn't, because these things typically all have bad reduction, or we don't have any reason for them to have good reduction. We have to deal with those as well. So no, the one that has to have good reduction is A. A has bad reduction. Well, for the Chabauty-Coleman method over curves, people have generalized it, but it really involves new techniques to get different statements.
Yeah, if there are no further questions, please thank the speaker.